So it gives me great pleasure to present Professor Ragni Piene today. Professor Ragni Piene is a professor emeritus at University of Oslo, a member of the Norwegian Academy of Sciences and Letters, and a fellow of the American Mathematical Society for her outstanding contribution to the creation, expositions, advancement, communication, and utilization of mathematics. Ragni Piene has been since 2003 a member of the Executive Committee of the International Mathematical Union and was for many years the chair of the Abel Committee. She is a Norwegian mathematician specializing in algebraic geometry with particular interest in enumerative results and intersection theory, which is the topic of her talk today. Thank you, Professor Ragni Piene, for kindly accepting our invitation.
Thank you. I would like to start by thanking the organizers for inviting me to what seems to be a fantastic gathering of Brazilian women mathematicians and male mathematicians. But I guess there has never been this many women mathematicians in one room before. So that's really fantastic. The topic, and also I should say, I'm always happy to be back in Rio, in Brazil, and especially at IMPA. So that's always a great pleasure. The topic of my talk today is counting problems and generating functions. So let's start with counting. I think people, since they were, people were people, used their fingers and toes as counting tokens. But also, 10,000 years ago, people had tokens used for counting. And you could imagine that maybe they counted the different tokens counted different things, or who knows? We don't know. More advanced ways of having ways to count was the abacus. You could also calculate with it. And there have been lots and lots of ways of counting. For example, using knots on strings in different colors. This kipo is from Machu Picchu Museum. I have to admit I do not know the meaning of the knots and the colors, but it's a beautiful object, right?
No one knows anymore.
I think nobody knows, yeah. But I mean, it would be interesting to know, actually. Project. But I'm going to start with something much more prosaic, namely let n be a positive integer. And partitions are going to be going through this talk. So there will be many types of partitions. Let's start with the sort of obvious one. How do you partition an integer? Well, you write it as a sum of smaller positive integers. And what you would like to know is if you take an integer n, in how many ways can you write it as a sum of smaller integers? So let's start. 1, indivisible, right? 2, there are 2 ways. 3, 2 plus 1, 1 plus 1 plus 1. Then we go on and we find not 4 ways, but 5 ways for the number 4. And you see, you can also look at bigger numbers like 7, and you're going to see that there are many more ways of partitioning 7 than there are of partitioning 4, of course. So what is this sequence that we get? We get 1, P of 1, P of 2 is 2, P of 3 is 3. It's not so very interesting sequence. P of 4 is 5, something's happening. And now you could ask, is there a closed formula for this number Pn? Can you write it as a polynomial in n, or exponential function, or something that you can actually just compute? And that's not obvious, right? You don't see the pattern, you don't see what the formula should be. But so you can do something else, and that's what Euler did. So Euler said, consider the infinite product of formal power series. So here you take the normal 1 plus q squared, etc. Then you multiply with 1 plus q squared plus q squared squared plus q squared cubed, and so on. Here you take 1 plus qm squared, and so on. So you have an infinite number of power series, and you try to expand it. So you write it as one power series. And what you're going to see, if you think about it, is that the coefficient of q to the power n is actually precisely this number we're looking for. It's the number of ways you can partition the element, the number n, in as a sum of integers, positive integers, of course. So what have we found? We have found that if we define the generating function for the partition function, namely the function which is a formal power series, q is just a dummy, I mean it's the variable. And Pn is the interesting thing here, so we take this formal power series where the coefficients are the number of partitions of n, and what we have just seen is that this generating function is just an infinite product of power series. And since this power series is the inverse of the polynomial 1 minus q to the n, we can write it in a short, compact way as this infinite product. So that's the partition function. That's Euler. Now, you could say that what is a generating function? Well, sorry. I always mess up. What happened? Sorry. I was here, right? Okay, let's go slower. So we have displayed a sequence, namely the coefficients of the generating function. And you see this is not such a bad sequence, actually. The numbers don't get too large. But, I mean, that's what we have. And, of course, if you have a power series, you can find a closed formula by taking the residue of the power series divided by q to the power n plus 1. But that's not, I mean, it's sort of cheating. It's not really a closed formula. It's just saying that we take the nth coefficient. So it's not really what we wanted. Now, the late H.S. Wilf, mathematician, was a great fan of generating functions. He wrote a very nice little book called Generating Functionology, which is available on the web for free. And what he said is that a generating function is a clothesline on which we hang up a sequence of numbers for display. So we need an infinite clothesline, but we can at least start. So here you see the beginning of some sequence, which you don't yet know what is, but you may find out if you stay awake. So now I want to look at a different kind of partitions, namely the set of plane partitions. And plane partitions are actually also just partitions of an integer, but we put them out in a plane instead of putting them out on a line in some sense. So what do? You take 1, you can still not divide. 2, you can have 2, you cannot do anything with that, but you can have 1 plus 1 written horizontally or 1 plus 1 written vertically. So those are 2 different plane partitions. And similarly for 3, you see you get the partition 2 plus 1 comes in 2 ways, horizontal and vertical, and 1 plus 1 plus 1 comes in vertical, horizontal, and then in the corner. So we get more plane partitions than ordinary partitions. And if we look at the generating function for the plane partitions, we get what's called the McMahon function, and that was because McMahon discovered this. So that's a result due to him. And you see the only difference with the partition function is that we have minus m instead of minus 1 in the generating function. So we get bigger numbers. And you can see, if you want to convince yourself that this is the right way of doing it, you can write out the first products here. If you only want to go up to Q3, then this is what you get. And then you can sort of see how you can find the coefficients. You have a Q2 here, but you also have 2 Q2 here, which corresponds to these two partitions, and then the Q2 was just the 2, and then for Q3, you see you can also see where these various coefficients come from. So altogether for Q3, you have 1 plus 2 plus 3, so you have 6. Sorry, no, for 3 you have 6, and for 2 you have just 3. So you can also encode your partitions by doing variables. You can think of that you have 3 variables, the z going up, the y going to the right, the x going down. So for example, here you have 1, which is just a 1. So this, and the 1 to the right, which would be y. Here you have 1, which is 1, and 1 to down, which is x. Here you have Q3, which is just 1 in the corner, and then you go up with z and z squared. So to each of these partitions, you can associate a monomial in x, y, z. Here is an example. You have a partition of 22, and these are the monomials that we get from this partition. Now let's count something else. So let's try to look at a word, so a collection of letters, and we have these words, and we want to insert parentheses. We take n plus 1 letters, and we want to insert n parentheses, and we want to know in how many different ways can we do that. So what do I mean? For example, for n equals 3, we have a word A, B, C, D, and we can insert parentheses in 5 ways. What else can we do? We can look at another problem, which is seemingly different. We take 2 endpoints on a circle, and we want to know how many non-intersecting chords can we draw through these points. So this was a game already the old Sumerians played. You see you have 1, 2, 3, 4 points. So this is the case n equals 2. And you have 2 chords here. Or you could take this chord and that chord. So there are 2 ways. The answer is 2 if n is 2. Or you can take a regular n plus 2 gon and ask in how many ways can you triangulate it. The answer is not easy to see, right? Especially if n is arbitrary. But if n is 4, you can actually work it out. And as you see, there are 14 ways of doing that. And now the question is, what is the general answer to these questions? And first thing is that they all have the same answer. It's the same number for all of these problems. And this is the famous Catalan number, which turns out up not only in these 3 problems, but actually in almost 70 sort of similar counting problems. And this is a list, I think, made by Richard Stanley. So they are really everywhere. So it's a Catalan number is 1 over n plus 1 times the binomial coefficient 2n over n. And what's interesting with this number, one of the things, is that the numbers satisfy a convolution formula. If you have either a convolution formula or a recurrence relation, which you can also think of this as, you can do something to the generating function. So for example, in this case, because of this formula here, if you look at CQ and you use this relation, you see that CQ is in fact equal to Q times CQ squared minus 1. Looks strange, but that's true. And if you solve this ordinary second degree equation, you get the solution for the generating function. So here you have actually a nice closed form of the generating function. It's maybe not so nice to have 1 minus 4q to the power 1/2, but that's the power series. It's all formal power series. So you get the formal power series, and the coefficients are precisely Cn. So this is possible to compute. Now I want to pass from sort of counting points or numbers to geometry. And simplest maybe model for that is to look at Schubert calculus. And in Schubert calculus, you look at intersections between linear spaces. And the typical question is to ask how many linear spaces of this dimension meet that many linear spaces of that dimension in some projective space. So let's do the first example in this case. And the first example is you take 4 lines in free space in general position. So they lie one here, one here, one here, one here. And then you ask how many lines meet all these 4 lines. And if you think space is big and these 4 lines are just out there somewhere, you will say, well, are you sure there are any lines? And yes, there are lines. And how could you try to compute it? You can say, okay, these very general lines, they don't have to be that general. Let's make them a little bit in special position. So take 2 lines and let them intersect, and 2 lines here and intersect. Then you get 2 points of intersection, and there is 1 line between those 2 points. So there is at least 1 line. Now, you could also see that if you have 2 intersecting lines, that will give you 2 planes. And you're in projective 3 space, and if you know a little bit projective geometry, you know that 2 planes in projective 3 space always intersect in a line. You can have no parallel things in projective geometry. So they intersect in a line, and this line of intersection are going to intersect your 2 line pairs. So you have found 2 lines, and that's all. So the answer is 2. So now you can go on and be more bold and ask how many lines meet 6 given planes in P4. And now your intuition say, I cannot imagine 4 space. I cannot. I mean, well, abstractly, but not really. I cannot put my lines. In this case, you have to have planes, and you could try to put them in special position and try to work it out. But it's not so obvious. The answer turns out to be 5. So now it should start ringing a little bell, because now I ask you, how many lines meet 2n I have n minus 1 planes in Pn plus 1. That's codimension 2 linear spaces in Pn plus 1. And I have 2n of them, and I ask how many lines meet all of those. So anybody guess? What can it be? You've seen it. Huh? Nobody wants to. What else? I mean, you started with 2 and 5. You should have recognized that. It had to be the Catalan numbers. So as I said, again, this problem have solutions 1, 2, 5, 14, 42, etc. This is what the generating function for the Catalan numbers displays. Now I want to pass from lines to the next simplest object in geometry, if we're talking about curves, and that is circles. I'm not going to dwell on that. I just wanted to show a picture. And this is Apollonius's famous problem of taking 3 circles in the plane. These are the black ones. And asking how many circles are tangent to all of them. And you see here this very nice picture, circles in different colors. Let's see, which one should we take? The yellow one is tangent to the little one here, it's tangent to the big one there, and to this one here, and so on. And they're precisely 8. That's not hard to figure out. Apollonius wanted also to construct the circles, not only to, but that's not the topic of this talk. So that's a very old enumerative geometry question. And now I have to pass, be a little more technical maybe. I want to talk about plane curves. So a plane, let me first define a plane curve. Now I'm over the complex numbers to make life easier. I'm in projective 2 space, projective plane, so I have to use homogeneous coordinates. So I have a polynomial which is homogeneous in 3 variables of degree d, and the 0 set of that in the projective plane is well defined, and that's what I call the projective curve of degree d. So to give you 2 examples, here is a conic, that's degree 2. Let me say that a curve of degree d has a genus, and the genus in this case you can just think of as the number degree minus 1 times degree minus 2 divided by 2. That's the genus. So if my curve has degree 2, then 2 minus 1 times 2 minus 2 divided by 2 is 0. So that curve has genus 0. Now, the other one, and we call a curve of genus 0, we call it rational. This curve has degree 3. Its genus is 2 times 1 over 2, which is 1. So it has genus 1. And most of you know a curve of genus 1 is called an elliptic curve. So this is not a rational curve. But I can make it into a rational curve. I just deform it a little bit, or degenerate it, rather, I should say, so that it makes 2 branches. You just pull so you have 2 branches cross each other. Then you get the simplest kind of singularity a plane curve can have. It's an A1 singularity. It's a normal crossing singularity. It is a singularity which diminishes the genus by 1. So if I start with a curve of degree, which this should have had genus 1 because it has degree 3, but since it has this singularity, it is rational. It has genus 0. So if I have an arbitrary curve, degree d, and I want it to be rational, I have to impose the correct number of singularities. So now, this is the only time I'll mention Gromov-Witten, because this is actually a very old enumerative geometry problem, is to count rational curves of a given degree. And by count, I shall be more precise. But this is actually sort of the basis, in some sense, of Gromov-Witten theory. But that's finished with Gromov-Witten. So now, if you want to see what the space of all curves of degree d, the dimension of that space is the dimension of all polynomials in 3 variables of degree d, homogeneous. And that's d plus 2 over 2, and then you have to divide by 1, sorry, you have to subtract 1, because you can multiply a polynomial by a non-zero constant, and you will get the same 0 set. So that's the dimension of the curves. And now, since these curves have genus d minus 1, d minus 2 over 2, you have to impose that number of singular points in order to get the rational curve. So if you look at the space of rational curves inside here, you will get a space which has dimension d plus 2 over 2 minus 1 minus the number of conditions you impose, namely d minus 1 over 2, and the answer then is 3d minus 1. So now you have a space. It's not a linear space. You have a space of dimension 3d minus 1, and you cannot count the number of curves in that space because it's infinite. So you have to impose more conditions. And you don't want to impose more singular points because you already imposed the maximum number of singular points you could have. So what you can impose is that these curves go through given points in the plane. So the big problem is find the number of plane rational curves of degree d passing through 3d minus 1 points. And you see immediately that if d is 1, you want the number of lines that pass through 2 points. That's easy. Answer is 1. For d equals to 2, you want the number of conics that pass through 5 points. Conics are rational. So the answer is 1. And for d equals 3, you want to know the number of nodal cubics, the one I had on my picture, that pass through 8 points. And that number is not 1, it's 12. And this is an old sort of discriminant result, which was known since way, way back. But it turns out that the higher degree numbers are much newer. And the big breakthrough here was Konsevich's recursion formula, which is rather complicated, right? And again, it's a degeneration argument that you break up your curve of degree d as a union of one curve of degree d1 and one curve of degree d2, and then you try to make some count, which is essentially what he did, but I'll stay far away from trying to justify this formula. What you see is a little bit disturbing here is that this is not symmetric in d1 and d2. It's a bit weird. You don't really have the same things. And if you want to know the generating function, who knows? I mean, this recursion formula does not lend itself easily to give a generating function. But what you can do, at least if you're a physicist, which I'm not, so it's not my thing, you can replace nd by this nd over 3d minus 1 factorial. And by doing that, you miraculously get a recursion formula which is symmetric in d1 and d2. So it's much easier to handle in some sense. And you can try now to make a generating function, and this is where you really have to be a physicist, because you say, you shouldn't have a generating function with just one variable. You should have two, and in fact, one of them should actually be an exponential. And the other one, which we sort of didn't have before, should mark the number of points, 3d minus 1. And if you do this function, you don't find the generating function, but I mean, this is the generating function, but which you don't know what is. But you can find that it actually satisfies a partial differential equation of this type here. So if you could solve that, you could say then you could find the generating function. But I don't know anybody who did that. So that's sort of how far you got along that line. And what I should say maybe is that there are no partitions involved here, except that you sort of divided your 1 degree into 2, but that doesn't really interest you. Okay, so this is in this case, what we want to display on the closed line is this sequence of numbers. And you see it gets really horrible numbers. You don't really want to know the numbers precisely. You just want to know the generating function, or you want to know a closed formula for the number or something like that. But that's sort of as far as you get. So then we have to try something else. So let's now do more geometry. We take a surface in 3 space of degree 4. Just think of it, it's given by a homogeneous equation of degree 4. Now you have a surface. How can you get a plane curve? Well, you just take a plane and you cut the surface. Gives you a nice quartic surface. And most of these quartic surfaces, C that I call them here, will be of genus 3, because 4 minus 1 times 4 minus 2 divided by 2 is 3. So you have genus 3 curves. Now I want to count rational curves, as always. And if I want to do that, I have to impose 3 singular points on this intersection. And how do I get singular point when a plane intersects a surface? The plane has to be tangent. It cannot be a transversal intersection everywhere, because then I don't get any singularities. So in fact, what I want is to count planes such that C has 3 nodes, because then C is rational. And that's the same as asking how many H are triply tangent to S. And now I'm back in very old enumerative geometry. Salmon in 1800 something knew that there is a formula for this. So if D is if D is the degree of a surface, then the number of planes that are triply tangent to the surface is given by this rather interesting formula. And if you plug D equals 4 into this formula, you get 3,200. So that's the answer, period. But you see, I say answer 1. So there is also an answer 2. And answer 2 say, well, we were doing all these partitions. And we had this partition function, and let's play around with the partition function. partition function to the power 24. You can start expanding it. Of course, you get 24q for the first thing. And then here you have to compute. There you get the same thing, 3,200. And of course, the interesting thing is that the 3 is here, and we're looking for 3 nodes. So there must be something. And now this is, I started at 2. So I have to be a little brief here, but let me just say that what you can do is to look at what's called K3 surfaces. The quartic surface is a special case of something which is called a K3 surface. And for a K3 surface, you can look at families of curves on the surface, and you can impose the number of singularities, which is the same as the dimension of this family of curves. And then you get a number, nr, which doesn't really depend on the surface and the number of curves, but it depends on the dimension of this system of curves. And the thing is, you get an nr. So what we just found is that n3 is 3,200. But you can do this in other dimensions. And Yao and Zaslow conjectured, and now you see the partition function, that the generating function for these numbers is precisely the 24th power of the partition function. And that's why we got the number we got on the other slide. And they almost gave a proof. Brian and Leung explained why this should be true. I mean, why does the partition function appear at all? And the reason the 24 appears because it's the so-called topological Euler number of the surface S, which is also the second Chern class. This the surface S can be degenerated to a surface with 24 singular fibers and the rest elliptic fibers. And if you want to count rational curves on such a surface, it has to do with counting this, how many times you can sort of map rational curves to these singular fibers. And this turns out to be a way you write the number r as a sum of not positive but non-zero integers j1 to j24. And then it turns out that each of these fibers get a weight, which is precisely the number of partitions of each of these integers. So I don't expect you to, I'm not giving the whole explanation, and I'm not expecting you to follow, but just, 24, yes, there is a reason, and it reflects itself in these singular fibers, and then there is a thing which says that you have these partitions, and when you sum them up, you should get precisely Pn to the power 24. Okay. So let me talk about something else, which are Stirling numbers. So now you're back to partitions. But now you take a set with n elements, and you want to just divide it into a certain number of blocks, and you want to know in how many ways you can do that. And if you do it in all the ways you want, if you sum up these ways, you get possibility of all partitions into blocks of different sizes, and this is what's called the Bell numbers. And the Bell numbers can be defined recursively, which means, again, that there is hope of finding a nice generating function. And here we don't use the usual generating function, but we replace, again, similarly to what we did in the other case, bn by bn divided by n factorial. And that behaves better in this setting. And so we get, if you use this relation, you'll be able to compute that if you take the differential of bq, just derive with respect to q, then you get eq, which is just e1 plus q plus 1/2 q squared, etc., times bq. So you have a differential equation to solve, and you can solve it, and you get very short way of writing the generating function. It's maybe not so illuminating either. But again, sometimes one is just happy if one has some closed formula for what you're looking for. Where do these Stirling and Bell things appear? They appear, for example, in what's called polydiagonals. So you know what the diagonal is. That's the set of the points where all the x's are the same. So you're looking at n tuples of points from x, and the set where all of them are equal, that's the diagonal. It's a small diagonal. It's isomorphic to x. But you can also partition these numbers 1 to n into disjoint subsets of different sizes, and you can ask that you look at points where the x's with indices belonging to the same subset should be equal. So you could have the first and the second, and the third and the fourth, the first and second being equal, the third and fourth being equal, and so on. So these subsets are polydiagonals of different dimensions. And the number of those that are of the type ik is the Stirling number SNK, and if you sum all of them, of course, you get the Bell number. And so the Bell number is also the number of all polydiagonals in the product xn. And you can find, I think I will not bother with that, but you can count how many polydiagonals there are of each type. So just briefly, here is an example with x equal 4. You have k equal to 2. You have 2 ways you can divide in subsets of size 1 and 3, or subsets 2 and 2. And you have 4 of the first kind, and sorry, you have 1, 2, 3, 4 of the first kind, and 1, 2, 3 of the second kind. So the Stirling number here is 7. And the Bell thing, if you sum for all k, you get 15, which is the fourth Bell number. So they appear naturally when you want to look at polydiagonals. Now you can also do Bell polynomials, which is more, you take these numbers and you sort of add variables. You get partial Bell polynomials. You can get exponential, the complete exponential polynomials by summing the partial Bell polynomials. And just to show what they look like, they're rather nice and simple. And they sort of grow a little bit like this. You note that you always have the highest sort of variable appearing alone at the end in these polynomials. And these polynomials are recursively defined like the Bell numbers. Similarly, you see you get Bell numbers if you put all variables equal to 1. So it's a polynomial way of doing the Bell numbers. There is a formal identity that you can write. And you can, as I said, see that you get Stirling numbers and Bell numbers by just putting all the variables equal to 1. Okay, for those who are tired of numbers, we can do calculus. And now I think I have to be, yes, quite brief. So this is Father Bruno, and we want to differentiate the composed function. We do it once, we do it twice. We use some notation in order to be able to write it. And now you see this looks almost like Bell polynomials. Now, what's going on? In fact, Father Bruno says that the nth derivative of h is given by the sum of kth derivatives of f times Bell polynomials of the derivatives of g. So that's another way where Bell polynomials appear. And it's interesting because if you have a family of curves on a family of surfaces, you can actually make a sort of recursion like you do in Father Bruno's formula in order to see that the Bell polynomials should appear in the generating function for the numerative problem, which is to find the class of the curves that have precisely R nodes. And This is something we did for, we conjectured, we proved it for r less than equal to 8, and Thies Laraker, who's a student of Martin Kool in Utrecht, proved it last year in his thesis for all r. So now that's good. And the recursion has to do, maybe I should just say it. You have a family with r nodes. If you blow up in this family one of the nodes, then you will remove a node, and you will sort of end up with a new family where the curves have one less node. And now, in order to find formula for the r nodes, you take the formula for r minus 1 nodes upstairs, and you push it down. And when you do that, you get this kind of relation, which you can treat as differentiation, and miraculously, the Bell polynomials appear. And I want to say this just because that's how we found in the beginning that the Bell polynomials had to appear in this setting. And another reason for Bell polynomials are the polydiagonals, which I will now not go into, but you can also look at these nodes in a different setting by taking the critical locus of the map of D to Y, and then again you will see that the Bell polynomials appear in a very natural way. So they sort of come in both from the polydiagonal side and from the recursion side. There are other ways of counting curves. I will only mention the last one, because you don't need to count curves on surfaces. You can count curves on higher dimensional varieties, for example, threefolds, especially Calabi-Yau threefolds. Or you can count sheaves or cycles on threefolds, especially on Calabi-Yau threefolds, and then you get into Donaldson-Thomas theory. And now I finally want to go back to McMahon. And we had the partitions, plane partitions, which we could view as monomials, such that the complement, all the other monomials would generate an ideal of co-length n. And we had already an example. This is case 4. We had this, which you have seen. And now the last minute, I'll tell you why the McMahon function comes in Donaldson-Thomas theory. So we count now the number of monomial ideals of co-length n, but monomial ideals are the same as the co-length n ideals that are invariant under the torus action. The torus here is c star to the power 3, which acts on this polynomial ring. But you can also geometrically say that that's the fixed points of length n of C3 under the torus action. And this is what is called the virtual count of the degree 0. I'm not counting curves now, I'm counting degree 0, of degree 0 Donaldson-Thomas invariants. And, oops, too early. I have to say this. So you see the McMahon function appears, but since this is a virtual count, it sort of appears with a sign. That's okay. The interesting thing is that we had the partition function for the two-dimensional analog of a Calabi-Yau threefold, namely a K3 surface. We have the McMahon function in the case of the Calabi-Yau threefold with very simple topological Euler number. So the thing is that if we have a Calabi-Yau with some other Euler number, then it should be this thing to that power. That's what one would expect, but I don't know. So thank you for your attention.
Thank you very much, Professor, for your, beautiful, colorful, and historical talk. It was very, very nice. Would you have some perguntas, comentários, questions, please? Yes, obrigado.
So, when you were talking about counting rational curves.
Yes.
There, and in your definition, you said that the rational or curve was
Oh, the rational
the
curves.
zero?
I thought you said
No,
real curves. No, the rational
no,
curves.
No, my
Sorry.
question is just because you transform one curve, zero of some polynomial of degree d, and then you just deform the curve in such a way that you have a node. And how you know that this new curve is still a zero of one polynomial?
You can actually, I mean, if you really want to compute, you can compute, but this is, this is not a problem. No. If you just look at all polynomials and you look at the zero sets, then you will find all these curves among the polynomials. Yeah,
okay.
so it's not, you don't really have to construct them, they're there.
Okay, thank you.
Questions, comments? Yes.
Good afternoon. I liked very much when you showed the conservative thing, but I wonder, do you have any explanation for it not being symmetric? You said none whatsoever, not even a guess, a wide guess?
No, I have to admit it's a long time since I sort of looked into his proof, and no, I don't, I cannot say anything about it. It's just interesting that when you change it a little bit, then it becomes nicer.
Please,
you have to read his proof.
More questions, please? Comments? Well, I just have one comment, please. Okay. Well, I think I have to ask and I have to comment about that. So, this year we had something very, very special because we had the first woman to receive the Abel Prize in 2019, Professor Karen Uhlenbeck. And as chair of the Abel Committee for many years, could you please comment on the prize for a woman, for Professor Karen Uhlenbeck, please?
Well, I cannot say anything from my own time as chair of the committee because that's not information I can share with anybody. I can just give my own personal opinion of this year's prize winner, which I thought was a fantastic event. And she was a very worthy winner, and it was a great pleasure to have her visit in Oslo, and it was really great. And I think we received so many positive comments. So it was really nice, yeah.
So any more comments? No? So, Professor, thank you again. It was very nice.
Thank you.